Hello everyone and welcome back. So this time we're still going through chapter 8 talking about bending. But this time we're going to get into some more crazy situations. Like what do we do if we have a beam that's not made of a homogeneous material? Because our flexure formula, that only works with homogeneous beams. And sometimes you'll have a steel beam that's being reinforced by wood or vice versa. So let's get right into this. Now, beams come in an assortment of shapes and sizes. One thing we need to think about is how does the shape actually affect their performance? And could we calculate the effect of the shape on the performance of that beam? Well, we're going to learn how to do that with a bunch of different types of beams today. So, using that flexure formula we calculated last time, the stress in any part of the beam can be calculated. Which is great. If we know what the moment is at that point, we can calculate the stress using our flexure formula, which is simply the moment times the distance from the centroid over the moment of inertia. It can also help us determine where we're going to need reinforcement, because if you see this bending moment right here, it's very, very high right there. There's also bending moment right here that's very, very high. And we're going to need some sort of steel reinforcement there to help with that, especially in these points where it's at a maximum. However, that is going to destroy things for us. Why is it? It's simply because it was only meant for a homogeneous material. We'll come back to that. But as I said, those beams, they come in many different shapes and sizes. If you look at these 4 types right here, which surprisingly enough, you'll be able to find appendices and tables of all of the properties. Which one do you think is most commonly used? The wide flange shape is actually most commonly used. Now, why is it a W instead of an I? I really think it should be an I. Come on, that looks like an I to me. But the reason we like it is because it's economical, and it's maximized the section modulus of the shape. We put most of the area very, very far away. We have a very thin web, and then a lot of area in the flanges. So, like I said, most of the area is there. Very little is in the web because that doesn't do much for our moment of inertia. And the strong axis is that horizontal axis through the centroid, while the weak axis is this vertical axis. Now, one thing to be careful about is that it's meant to take a load that's bending it around its strong axis. Remember that. It's meant to take a load that's bending it around its strong axis. It's not meant to take loads that are bending it around its weak axis. It will fail much more quickly in that regard because its moment of inertia is very, very small then. And that will lead to very, very high stresses. So, strong axis good, weak axis bad. Okay, but as I said, all these can be found, you can find parameters of these in the appendices. And it's much more accurate to do it using appendices because that will take into account all the fillets and rounded corners that you can't really see. You'd have to approximate it with like triangles or rectangles when there's definitely some rounding in there. Now, let's talk about how we can design a beam that's going to be strong enough to hold the loads we're going to be putting on it. Now, one of the ways we can do that is to through the section modulus, which is simply the moment, bending moment, is simply our moment of inertia over our distance to either edge. If you're wondering why to the edges, it's because our max bending stress always happens at an edge. So, using this, we can figure out the minimum section modulus required to hold the stress. Why minimum? Well, because you could always make something bigger and stronger, but at some point you're just wasting money. So don't waste money. Make sure that you're actually pushing forward to have the cheapest but safest creation you can. And so you would be looking at all those tables I talked about earlier for all the different beam sizes, and you would find one that has a section modulus that is perfect for your situation by looking at the internal bending moment and the allowable stresses. So what you'll do though is you'll scan from the lightest members with the lowest section modulus until you reach a shape with a suitable section modulus. Normally it's the lightest beam that'll be chosen, but not always. Okay, jumped a little bit too far. So that will end it here. Now, this section modulus thing is a great little detail. I don't use it all that much in this class. Not saying I don't calculate the section modulus, it's just I very rarely will give you problems where you're having to run to the appendices to do this. But don't forget that they exist, okay? Don't forget that the appendices exist. They're there to help you. So thank you for listening, and next time we're going to jump into how we use that flexure formula if we have a beam made of multiple materials. I'll see you then. Have a wonderful day. Goodbye.